get going. Okay, we're on lecture 25, and we did skip lecture 24 last week. So lecture 24 was about something called union find. It's a completely other way to determine connectivity. It's kind of funky and different than most of the stuff that we've been doing lately. But it's actually very, very fast. So you'll see some remnants of it in the course, but I'm not going to test this on it. But if you go out into the world and you hear about something called union find, you should think about connectivity. So union find is a very, very fast way to determine whether two things are connected to each other. It doesn't ever give you a path between those connectivity points. It's just sort of like if you're in your house somewhere and you got somebody in one room and you're in another room and you want to know if those two outlets are somehow connected through the house, it's a yes or no question. And that's what union find would do for you. So unfortunately, we're not going to really have time to fit it into this course. So maybe in a lucky way, that's just one less thing that you have to worry about. But you might hear about that sometime down the future. Now, I did move this out for both the quiz and the homework 6. So you got an extra, not due tonight, due Thursday. Why would I do Thursday? Goodness, I try so hard to put all this stuff in there and get it updated. That is due Thursday. So not tonight, Thursday. So you can take a breath if you were thinking about doing it tonight. So sorry about that. And we have no lab tonight either. So hopefully it gives you a little bit of breathing room on the stuff that you're currently working on. And then we'll have a lab 26 on Thursday. But that's about it. And then we have Thanksgiving next week. So in 2 weeks, we'll have our next assignment, which is somewhat similar to what you're working on right now for homework 6, but we'll be asking questions about directed graphs. So right now, you're fundamentally thinking about connected components in an undirected graph. Today, we began our discussions around directed graphs or digraphs, which use sort of arrows that go only in one direction. And we'll be asking tougher questions like, are they strongly connected components? So right now you're thinking about connected components, little islands. But when we have directed graphs, as we see, it's going to be a lot more challenging to figure out if they're connected or not. Yes. Yes.
So is it due next week or the week?
Oh, 2 weeks. Sorry. Ooh, yeah. Sorry. Thank you for pointing that out. I'm always dealing with it's the Tuesday before Tuesday after Thanksgiving. Yes, thank you. After. Yes. Thank you. I was afraid you were going to tell me next week is not Thanksgiving, and I was going to really be confused because that has happened before. All right. So anyway, we'll be doing directed graphs, talking about strongly connected components. We'll talk about that briefly today, just to give you a flavor of what that is. And there'll be quizzes out there on all that stuff like usual. Okay. So we're going to lose another lecture next week. So there will be no lecture 28 on November 27th. That's another one that I had to really think hard about to get right. So we'll just try to, get the right amount of content into our lectures so you don't get completely buried, because I know everybody's got stuff they got to do on Thanksgiving holiday. All right, so the review for us, we'll just sort of skip this thing here, but think back about all the classes we've covered in the last really handful of lectures. We created a graph class and a paths class. We created a connected components class. Both of these classes are based on this graph class there. And the L1 or L21, that gives you the lecture number if you need to go back and refer to these things. Connected components, bipartite is a class we created for determining whether a graph is of the bipartite nature. And then cycle finder for undirected graphs we looked at, and we'll look at, if we have time, a cycle finder today for directed graphs, which is a slightly different problem. And we'll skip the union find. So we're just sort of packaging these little algorithms into their own classes. And the common base to everything, of course, is the graph. And you should be seeing that and getting somewhat familiar with that and working with your homework 6 so far. Okay. Now I'm going to skip over all the Union Fine stuff. This would be as if we had covered this. So I'm just not going to go into it, but it's here if you want to kind of read a little bit about it. You're welcome to do that. But as I said, we're not going to be covering it in this class this year. Okay? But it's a whole other way to actually build and solve problems very, very, very quickly, which is pretty cool. So for today, though, we're going to introduce Homework 7, and this is kind of a retro reference, but Crazy Taxi's been around for a while as a game. And we sort of mirror that in our Homework 7 coming up. I call it Crazy Town. We're basically going to build a bunch of connected towns with one-way roads, and we have to answer some interesting problems about that ginormous graph. So we'll write some code to answer those questions. And it's going to reflect a lot of the code that we're going to go over in class. So just like homework 6, where you're kind of copying code in from our class projects and then applying it to a problem, you'll be doing the same thing for homework 7. So, all the code, pretty much all the code will be written for you. So directed graphs is what we're covering. That is very often referred to as a digraph, and we're pretty much going to use the same data structure to represent digraphs. It really is a very simple change to our underlying graph structure. So that graph class is going to get modified slightly. We'll go through that here briefly. And then we'll study shortest path briefly and topological sorting. So topological sorting is a new concept and a really important one that we are curious about for what we call a directed acyclic graph. So it's going to be a digraph, but it's more like a tree, a directed tree that takes you always outward toward its leaves. And topological sorting is a really important characteristic or a byproduct of those graphs we want to figure out for a couple real world examples we'll talk about. And if we have time, we will look at finding cycles in digraphs, which is a little more difficult than what we had talked about previously, a little more complicated. So we'll see if we have time for that. Okay. So let's briefly look forward to homework 7, even though I know you guys are working on your homework 6, many of you. Homework 7, we're going to have this kind of large scale bubble view of these neighborhoods. Now within each neighborhood are a lot of connected nodes. But essentially, those neighborhoods are going to be what we consider to be strongly connected. And we're going to study that problem here over a couple lectures. But strongly connected regions of a graph are kind of like an island with bridges connecting them. It just so happens that when you're on any one of those islands, you can get from any house to any other house in some possible way, even if it's not direct. So we would consider that to be strongly connected because no matter where you go on this island, you can always get back home again. Now, there are bridges between these islands that are weakly connected, and there might be one or more of them, but those bridges, if you cross them, you can never get back again. Okay, so that is one representation of a weak connection. And so if we were to give you a giant graph and say, okay, figure out what are the neighborhoods that are strongly connected and not strongly connected, you would need a pretty clever algorithm to do that. And that's exactly what we're going to study here in the next couple lectures. So homework 7 is applying that algorithmic solution to this crazy taxi town problem. And so the problem is stated kind of hopefully in a fun and creative way, but if we boil it down, it's just a strongly connected component thing. So we have 1,000 residents connected by one-way roads. Everyone wants to visit everybody else, but we have people getting lost because they're crossing these bridges, not knowing that they can never get back again because all of their streets are one way. So we would like to identify safe neighborhoods, and that's just another name for strongly connected components. Okay, the neighborhoods where we can travel anywhere we want and not worry about accidentally crossing a dangerous edge such that we can't get back. So we want to find those neighborhoods, whatever they are, and then we want to also identify what are the houses that are connected. So the node numbers that are in those neighborhoods. So those two kind of go together. If you find the neighborhoods, you kind of know who's in that neighborhood. And then we're going to strip out any of the individual neighborhoods that really are all by themselves. Okay, so an island of one, even though technically it's a strongly connected component, we're going to leave that out of our analysis, right? So all these orange ones basically would be left out. So that's fundamentally all we're after inside of this particular homework problem. And so there's a couple add-on questions. One is, can we find a cycle in any of the neighborhoods, one or more neighborhoods, where we can paint the lines all in one go? So that is what we call an Euler cycle. So if you remember, we briefly mentioned that if you can find a path or a cycle that loops around and touches every single edge, that's an Euler cycle. So we want to know, can we paint all the roads with our painting truck without ever retracing any of the roads and end up back where we started from? Okay, so which neighborhoods have an Euler cycle? That's the question that we also want to answer with this particular problem. Okay, and there will be a number of graphs here laid out in a relatively similar way to, in terms of the data, to what you're seeing in homework 6. So if I just click into this briefly, it's trying. Let's see if it brings it up. It's a lot of data. There we go. So we have these arrays at the bottom. These are just data arrays. So we have a very large graph structure called Crazy Town Roads. Then we have a couple Euler graphs, so you can test your Euler code. And then a very small graph called a tiny DG and a medium DG. These are just allowing you to kind of make sure that your code is working properly. Okay. And so all of the code, like homework 6, will get injected kind of here and above and below, and all of your data is here waiting for you kind of down below. So you'll have to build these graphs, based on what particular graph you're trying to solve. Okay. So I've kind of packed it all in so we can fit it in one main.cpp file. Ideally, these would be different data files, but at least this way, you don't have to worry about your file IO stuff, okay? But that's our homework 7. So all that is there for you now. You can do it in Pro or in the online compiler or in Replit or something else. Feel free to download that, whenever you get a chance. Please do read your Canvas pages because there's a little extra information there that you might find helpful, okay? So that's 2 weeks out, considering that we'll be off for the Thanksgiving holiday. So it's coming a little faster maybe than it seems. Okay. Any questions on that so far? All right, well, we'll come back and touch on that probably Thursday, maybe Tuesday of next week at the latest, depending on how far we get in all of our lecture stuff. So, but that kind of lets you know where we're going. Okay. All right, so let's talk about digraphs in general, short for directed graph. So digraph is very similar to what we've talked about. And we're really curious about 2 things now, in degree and out degree at every vertex. So previously, in degree and out degree were the same because every edge was unidirectional. But now those values could be different. So that's a very important distinction. And it's going to be a clue for a number of algorithms that we're going to study. So there's no real root to this if it's a graph. Generally, it's going to have some cycles, but not always. If it has no cycles in it, we say it's acyclic, and it's a directed acyclic graph, which is often abbreviated as a DAG. So I used to hear people talking about DAGs very early in my software career, and I actually couldn't remember what they were talking about. And it really is just a directed graph where there are no cycles. So we call that a directed acyclic graph. And we'll see some examples of that. But if it has cycles, there's a loop in there somewhere. And we're always going to be traveling along some kind of a path. Now, we could have an edge that goes from C to L and then another edge that comes back from L to C. That's okay. They're both directed. We would say that they are both directed in that particular case. Okay. And we want to keep track of the in degree and the out degree as best we can, but it can be sometimes a little bit expensive depending on what our underlying data structure is. If it's an adjacency data structure, well, we're only really keeping potentially the outward adjacencies from any particular vertex like we've been doing so far. So it might be a little expensive to calculate the in degree depending on that particular data structure. We could create a reversal of the graph and keep two copies of the graph around at all times so that we can go backwards. But, that's just one possible strategy, okay? So these are truly network models because many real world things are actually represented by these directed lines. So just real quickly, because we're going to come back to it, here's our H with an out degree of 1, right? So notice we got an arrow going out, two arrows coming in. So that's our in degree of 2. If we reverse every edge and produce the reversed graph, which some algorithms rely on, then we now have, of course, an out degree of 2 and an in degree of 1. Okay. So just kind of introducing you to the vocabulary here. We'll be using these kind of as we go forward. So lots of things are certainly based on digraphs. We've kind of mentioned the idea of a map, and especially where we have one-way streets. So a one-way street is probably a little more familiar to us as drivers in the city. Also, political blogosphere. This is one that comes up a lot. Basically, these are relationships or references to this is way back in 2004, politically biased blogs and how they are referencing between each other. Transactions between a bank. These are, of course, directional. Where's all the money going? So some of this has been used to sort of analyze the bank crash 2008 you may have read about or possibly remember experiencing. Electrical circuits can be considered to be graphs. In this particular case, they don't always have cycles. They can have cycles in them electrically, but simpler circuits like this are DAGs or directed acyclic graphs. The data always flows in one direction. That's an adder right there for folks who have done that kind of stuff before. And then there's stuff that have feedback loops. So our canonical latches or memory units actually have some feedback loops. So this would be a cyclic graph if we were to sort of model it that way. And lots and lots and lots of things, right? We won't go through all of them, but in software, if we want to know whether we're going to have dead code, we might want to track where all of the address jumps occur when we jump into a function or try to go to a section of code in via a for loop or if-else statement. And things that we can't reach are kind of like those lone neighborhoods that no one can get to, right? So analyzing that kind of a graph would let us know that we have dead code somewhere in our computer program, right? Oops. So lots of examples there. Some of them, like scheduling your classes, they're graphs, but they are acyclic. So if you think about, what order do you need to take your courses in, and so you can get your prerequisites in, it would be insanity if one prerequisite was based on something you can't take yet, right? Because of a prerequisite. So that kind of a graph would not be, viable for a college. So all of the prerequisites for a college set of courses need to be a DAG or acyclic graph. Right? So we'll look at that idea in terms of what we call topological sorting. We'll get to that here shortly. But another one of my favorite graph representations is a state machine. I love state machines, especially if you're thinking about robotics or any kind of a functioning system like a computer, right? There might be a lot of things going on in the sleeping bubble, but we might want to model the state that we are in as a program by just sort of conceptually creating this graph and only allowing us to transition between states when certain conditions occur. So we'll come back to this idea of a state machine in a couple of weeks here before the end of the course. when looking at one of the algorithms. But you could certainly do a lot of things with a state machine to try to model the states of a particular autonomous vehicle or something like that. So let's take a look at the implementation we're going to use. It's really not too hard. There are some typical questions that we want to ask about one of these digraphs. One of the things is there a path? And is there more than one path between 2 points, right? So between A and M, can we get there? Yes or no? And is there more than one path? And how hard is it to find all possible paths from A to M? So there are a number of algorithms there that we could apply to answer that question, depending on how much information we need. If we just want to know, is there a path, yes or no, that's a relatively straightforward one. If we want to know what are all the paths, that's a little more difficult question. Okay? Shortest path, we'll look at this one here briefly. We looked at 2 algorithms for doing that. Topographical or topological sort, we have not done this before. That's us trying to figure out the order of the classes that we need to take. Transitive closure, which pairs are connected in both directions. So the idea of transitive closure means, can I get from A to H and H to A? That would be transitive closure by any pathway, right? It doesn't have to be direct, but that would be a transitive closure of those particular vertices, okay? Strongly connected means that all pairs of vertices in a particular area of the tree have transitive closure. In other words, a strongly connected component, okay? So if we could get from A to N and N to A and do that with all possible pairs, then we could declare that this whole thing was strongly connected. But we can kind of see pretty quickly that this particular graph doesn't have that feature for all pairs. So we would not call this one single strongly connected component. We'd have to do some analysis to do that. Now, there's some terminology out there that you may have heard of, PageRank for websites. This is just another name for the incoming or in degree of references or links between all the pages that are out there on the World Wide Web. Okay? So some of these terms we'll see, sort of typical academia references, but we sometimes see them in other ways out in the real world. A DAG, does it have no cycles? If it has no cycles, then yes, it is a DAG, okay? So no cycles in a directed graph means it's a directed acyclic graph, okay? So those are some of the major terms we'll kind of be covering in these things. So let's just kind of jump in just briefly. I know we're kind of running a little bit behind, but this isn't a coding one. But take a look at the D/U, so directed unweighted graphs, and take a look at the highlights here where it just shows you whether a particular thing is a DAG or not. So this is not a DAG because it's undirected. So let's go to our DU, right? So here is a DAG, right? A directed acyclic graph. So we got arrows, right? Nothing loops back around. So that's just one of these examples. You can pick a number of them, see if it's a DAG or not, right? This one is a no, right? So this is not a DAG, and probably because we go from 1 to 3 to 2 to 1. So there's at least one cycle there, right? 4, 5, 6, 7, 4, that's another cycle. So you can kind of see how that stuff it exists inside of one of these graphs, okay? So maybe poke around there a little bit and just get familiar, right? Eventually we'll talk about weighted directed graphs, but you can see the different categories, right? Undirected, weighted, which we have not talked about yet, and DU, that's what we're on right now. And we'll eventually talk about DW, which is the directed weighted. Okay? So these would give you all of the directed unweighted graphs right now. Or yes, directed unweighted. Yeah. Okay. And it's going to randomly give you a different one every time, but you can kind of go in here and edit these if you want. So I could say, for example, add a vertex or pick an edge. And I think if I just pick it and hit the delete key on Windows, then that thing is deleted. And so you can kind of play around with that, get your bearings, and use that if you need to try out some stuff. Okay. So on the Mac, it's a little bit different. You have to hit the function key to delete an edge or a vertex on this particular website. So Windows and Mac, it's a little bit different in case you're trying to do that on your own laptops. Um, but do try at least to kind of grok the idea of the DAG versus not the DAG by destroying cycles. So you can go in and find edges and delete them until something ends up being a DAG, basically. Okay. Okay, so let's see. Here's a couple others, right? Not a DAG because we have some cycles. I think we saw this in there. Mostly self-evident. Okay. Let's look at our API for this. So what is our application programming interface, or in other words, our interface to our class? It's essentially going to be the graph we've already used. We're just going to add a constructor argument and a data member that indicates whether it's directed or not. So now we have this sort of second argument in our constructor. By default, we probably were treating that as false. Now it's going to be true, it's directed. And when we add an edge, we'll no longer add both adjacencies. We're only going to add one adjacency now. And we'll look at this edge code here in just a second, but it's going to be a trivial change. In terms of our C++ language, I just want to highlight again, when we're doing this with dynamic memory in C++, new, right, always gives a pointer. So new graph gives me a pointer to a graph. That's why this variable says I'm a graph pointer variable. And when in C++ we have a pointer to a graph, we use an arrow to get to its methods or data members, okay? So up here, mygraph.addEdge, we use the dot here because I have no new. See, there's no new up here, okay? So this is what we call automatic or stack-based variables in C++. These are on the heap. I'm not trying to turn everybody here into a C++ guru, but we kind of run into this new versus automatic. I use the blue colors to help, reinforce what's automatic versus the orange or kind of pointerly purpley, or sorry, reddish colors to indicate we're dealing with dynamic memory, okay, or some kind of pointer logic, okay. So hopefully that, will ring a bell if you see these different syntaxes, and I can help you kind of work through that. But we're still going to be creating a graph, right, through the constructor and then calling methods on the graph to add those edges in our main loop, okay? So here is the actual code for that. Same stuff we saw before. We have this new is directed, and it's coming in through our second argument. We're going to initialize the data member here, right? And then we'll do the same kind of thing in our second constructor down here if necessary. And, and then we have our methods down below, okay? So we're going to modify the add edge method, and I'll show you here immediately how we're going to actually do that. So whether you call it from main or you pass in an array of edges, we'll have a slightly different behavior on that. Essentially, we're always going to add in the direction of A toward B, right? But we're only going to add the other one if it's not directed. So if it's not directed, we'll do what we've been doing all along and add this second adjacency, right? But otherwise, we're not going to do it, okay? So this second arrow is only going to happen in an undirected graph. Since we're moving to directed equals true, then we're really most of the time only going from A to B. The direction's kind of important. The first argument will be pointing in the direction of the second argument. So when you're doing your graphs for your homework 7, you'll not want to flip those around arbitrarily because you'll get a different result than probably what I'm expecting you to have, okay? But that's it. That is really all we need to do with our graph class for it to work for our directed graphs, right? Just adding one adjacency for our undirected. So when we were doing undirected, we had a very full graph here like this, right? So for each edge, 1 to 2, right? 1 to 2, right? And then 2 to 1, we had some repetition there, right? So we can kind of go through all the pairs and see that every adjacency is there twice, okay? In the the directed version, it's a much sparser representation, right? A lot less data because we don't have arrows going in every possible direction, okay? This is probably where our adjacency model really comes into its own because it's pretty lightweight. A lot of graphs don't have, highly dense connectivity, right? We have lots of nodes, but maybe not super dense connectivity if they're directed graphs. Okay. So a lot less waste in our representation. Okay. So if we were to try to do reachability, though, we still have the same kind of approach, right? So depth first search from S is one way to actually find whether we can reach some particular location or really any vertex in the graph. So a depth first search would work. A breadth first search using the Q would also work, and that would give us the shorter path, okay? So all of that code we wrote for the path class just works, does not need to be changed because we just have fewer arrows, I guess you could say, okay? So that's a really good thing, okay? So our reachability algorithm starts from some location. We, use our from vertex to track how we got there, and we'll have our was visited as well. All that stuff's really going to be the same as it was before, okay? Just fewer connections. So let's just take a look real quick at the code change for the graph. I'll kind of speed us up here. You don't have to kind of run through all this exercise, but let's just get a little familiar with where this lives in the code. And then we'll jump into the more meatier stuff. Waiting for this guy to finish loading here. Let's try that again. And again. Third time's charm. Nope. I know it's there because I did. So if you've got it, you can search for the TODO just to kind of see where those changes are, right? So here's our is directed, right? So I'm just going to tie that in, underscore is directed, right? Copy paste, do that in my second constructor down here. That's my first constructor. Oh, here's my first constructor there. Do it up there as well, okay? And then if we go to the add edge, right? So if is directed, okay? And remember that when you're inside of a class, you can refer to your data members directly in C++. But if you want to be really clear, you can say this arrow. So that's me, this instance, arrow, my directed data member, okay? It's redundant, but some people like throwing that in there. So if you ever see that, you'll know what that means in C++. Okay? So that is our kind of update to the add adjacency. And I think that might be all, but let's go see if we have any other triple questions. So really when you call your graph, you just got to remember, do I want it directed or not? Yes, I want it directed. And then that variable can be passed directly into my constructor. And that's all we have to do. Everything else basically works the same as it did before. Okay? So I won't take you through the interactive thing here, but you can build your own graph, of course, and test out all of the path stuff we talked about last time. Okay, so that's our kind of basis for where we're going for the next couple weeks. And you can work with any of these graphs. This is just the one that we used last time to test shortest path. So just kind of put that up there again in case, anybody wanted to try that out, okay? And I think I said this before, but all of our input sequences, you can either put them in individually or you can just kind of copy paste all of the graph in as one line. So a lot of times, obviously, you'll see me just pasting everything in 6 and then the pairs of connectivity to build the graph. It's a little faster that way, okay? So that is our change to graph. Okay, relatively simple to do. Now, code execution, I think I mentioned this, but oops. So one application in code is to use this idea to determine whether we have dead code in code that we've written, right? Maybe we want to remove stuff, or maybe we want to find if there's an infinite loop. That might be a cycle detection, and we'll look at that if we have time today. Another thing that's really interesting and a use of these directed graphs is garbage collection in languages like Java and Python. And this is a really fantastic Stack Overflow discussion about what it means to be on the stack and on the heap. But basically, we use an idea of reference counting very often. So the vertex in our graph would be some instance of memory usage pointed to by something, right, in code. And every pointer that refers to that thing would be an edge. And so if anything becomes untethered, right, unreferenced without an edge, sort of floating freely out there, then it becomes a candidate for the garbage collector to come around and return it to some pool of memory that we can ask for later on. And that's typically done with things that are on what we call the heap, right? They're all just sort of floating out there in memory somewhere. So this would be another great example of, using a digraph to kind of keep track of that stuff and keep things in order. Okay. And we can use all of our pathfinding things and depth first search to determine that, whether it gets collected or not. Shortest path, very briefly. So again, just showing you the same algorithm we looked at before is still working, right? We just track through the queue, right? We fill in where we start from, and we take out what's at the front, put its children in the back, and we just sort of keep going and tracking how we got to everything, right? So we update our from vertex using that queue. And we treat the length of every edge for the moment as being equal distance. And so that's a relatively simple algorithm. Okay, so that does not change at all from when we worked on it with the undirected graphs. Okay. Let's talk about topological sorting. So this is the kind of new topic for the day. So this topic only makes sense when we have a DAG, a directed acyclic graph. So think about it in terms of the classes you need to take and the prerequisites. So there's got a number of tasks, a class you have to take or something that you need to do before you do something else. And typically when we represent these with graphs, the directed edges point to the next class you're going to take in a sequence. So it can be a little confusing because sometimes, we get flipped around and we think of them in the reverse order. But in our scenario, if these are all of our classes and we've assigned some vertex IDs to them, the question we typically want to ask is, okay, here's a graph. What is the topological ordering? Well, first off, we hope there's no cycles in that graph. So at first glance, we might not be able to see that. So we might need just a special algorithm to make sure that there are no cycles. Like we should be able to have a graph of all of College of Marin's classes and say, hey, I sure hope there's no cycles here. And then we could do a topological sort on them. Like, hey, what is the order in which I have to take all of these classes? So, but what's the algorithm that we can use to actually figure this out? Well, one way to think about it, at least on paper, is to sort everything so that all the arrows are pointing up, right? So the thing at the bottom would be the thing that has arrows pointing up and there's nothing below it, okay? So this would mean that in this particular situation, we would take introduction to computer science first, and then we could take advanced programming or number 5, scientific computing, or number 2, AI, in any order we want, right? We could go to 6, right, as our second class, or we could take 6 and 5 and 2 concurrently. So all we're really saying with the topological sort is, what is the order I have to take it? But there are a lot of possible orders as long as I start with 3, okay? And 6, of course, has to come before 4. Okay, so 6 advanced programming comes before cryptography. Okay, I don't know if that's always the case, but in this graph it is. So if I were to say, hey, what order are you going to take your classes? List them one by one. There are multiple correct answers to that. Okay. So one confusing thing about the topological sort is that there are multiple linear sorts that would be correct, assuming we're going to take these classes one by one by one. Okay. So keep that in mind as we go through this, because some of us will get a different answer than others, and that's still okay as long as we've not, broken any kind of prerequisite requirements. Now, there are two primary algorithms for solving this problem. One is depth first search, and it was more or less formalized by somebody named Tarjan. And so we're going to dig deep into this one. Basically, we're going to do kind of what you're doing in homework 6, which is visit every unvisited vertex and begin a depth first search. So it's really similar to what you're currently doing, but we're going to do it in a post order traversal. We'll review what that traversal pattern is. And once we do that, that will essentially give us the information we need to determine the topological sort. It's kind of like saying, if I do a depth first search, the furthest thing I reach is probably the thing that I don't want to start with, right? And it's a little bit of a simplification, but we'll look at the code for that. There's also another queue-based approach that was formalized by somebody named Khan, and this basically requires that we calculate the in degree of every vertex. So that's the primary cost of this particular approach. And then we're going to use a queue to essentially select out the vertices that have no incoming edges. In other words, they have 0 in degree. So those are going to be the vertices that are probably the ones that we want to process first. Okay. Or last. Okay, so we'll look at that in brief. Okay, so we're going to process from the front of the queue and just keep repopulating things that have 0 in degree. In other words, nothing is dependent on them. There are no prerequisites. Okay. But let's dig into just a visual experience on these real quick. Go to Visual Algo and go to DFS BFS. That is the area top level, and it's a slightly different picture. I don't know if I have the picture here. I don't think I have the top level picture, but let's sort of jump into it. So DFS BFS is where we kind of have a variety of traversals. Topological sorting is a version of that. So if this is a DAG, we should be able to do a topological sort on it. Okay. So when I say I would like to do topological sort, it's kind of telling you, hey, do you want to use the DFS Tarjan approach or the BFS Con? So this is a good place to sort of anchor your understanding of these things. And if it says, hey, sorry, it's not a DAG, then that means we just, we have a graph that has cycles in it, right? And we can kind of see that here. So it's not very exemplary. Let's go over here to something that says it is a DAG, right? So there's a DAG. I think there's another one here that's a DAG, but we won't go there. So we'll just then do a topological sort on that. So we'll just run that. We'll dig into this algorithm here in a second. But you can see it's going to recursively travel down a particular path. And when it gets to the bottom, it's going to sort of enumerate on the unwinding recursively and slowly build up a list. And we'll go through how it builds up that list. But when we're done, we will have one of multiple possible answers. So this is saying right here, I know it's really small, but if you run this on your own computers, it's saying 76012534. That would be the order in which you can take these classes, right? So in other words, it's saying class number 7 is guaranteed to be the least, it doesn't have any prerequisites, right? We can kind of see that that doesn't have any prerequisites, okay? And then we take 6 and then we go to 0. So similarly, 0 has no prerequisites. So we could have started with 0 and then gone to 7. That would have been perfectly fine as well, right? So it's just like, think about taking your classes. You could do these, English prerequisites separate from computer science prerequisites. as long as you kind of don't violate any of the prerequisite rules, okay? So that's our BFS, and you can kind of dig into both of those and play around with them. We'll learn the DFS version, and I'm going to leave the BFS out there. We're not going to really do a code implementation for that. It's kind of a good quiz slash test question. So we'll touch on it briefly, and I'll give you fair warning if I decide to throw it into a quiz or a test. You'll know before it kind of comes out, okay? But let's study this depth first search approach, this Tarzan approach, and review what we mean by post-order traversal. So with a post-order traversal, it means we explore the children before the parent. The P parent is post or after. So we go left as far as we can go, we unwind and go right and go left as far as we can go, etc. We explore all the children first, and when we've run out of children, then we write down the name of a parent and continue. So let's study that. So the first thing we're going to do is recurse all the way down to the far left, right? So we're multiple levels deep in recursion now, and we print out before we unwind. So we say, okay, print out the one, okay, unwind. Don't print out the parent, try to go right. Okay, there is no right. So now we can print out the parent. So that's a 3, okay? Go as far right or left as we can. Print out that, unwind, print out that, print out that. Go as far left or right as we can, right? So we go all the way back up to the 9, right? Then recurse back down again. It's a weird one, right? It's just one of those 6 flavors of reordering the recursive calls. Left child, right child, then parent. Very simple change in code, but it gives us this very unique traversal structure that is essentially going to give us the children before it gives us the parent. And that's the key to the Tarzan algorithm. We're basically saying, hey, we want to visit the children first in some dependency graph that is acyclic, and we'll sort of write them down as we unwind, okay? So that is a post-order traversal. And it turns out that if we were to then read it from the bottom up, right? So this is our post-order traversal, but if we read it from the bottom up, that is the order in which we can take our classes. So now we can see that kind of obviously from this tree structure because we've chosen a relatively simple graph here. But, you know, we got to take 9 before we can take class 5 or 13, okay? But by following this algorithm, no matter how complex the graph is, we will always end up from the bottom up with a listing of the least dependent things first and the most dependent things at the end, okay? And so we might end up like if I were to swap the 3 and the 6 branches and the 6 was on the left-hand side, right? Well, then we'd probably end up going down the left side first. And so 6 would happen before 3, but it would still be a valid answer, okay? It would still be the topological order going from that way up, okay? So this is the key to the code we're about to look at, okay? So I just wanted to give you the visual on that. Okay? I will remind you, you know, where that LRP thing comes in. Okay. Now the Q1, I'm just going to touch on briefly. So we're not going to do this in class. I'll let you know if it ends up being a test question. But here we're computing all of the n degrees of the graph, which takes some time if all we have is an out degree adjacency list, which most of you should be getting familiar with now, okay? So we'll add the vertices that basically have degree 0, incoming degree 0 to the Q. And then we say, while the Q is not empty, pop what's at the front of the Q, and then add the U to some topological list. So we're using a Q to build our topological list here, right? We're not putting it back into the same Q, we're just putting it in a list of things. And then we recursively follow all the adjacencies. Right? We'll delete an edge from U to V, and then we will see if there are no incoming edges, then we'll add that thing to the Q. So we basically just keep processing stuff until the only things that are left in the queue are the things with no edges. Okay. So that's the con approach. Okay. We're not going to dig too deeply into that, but you can kind of study that over here on that link that we just saw on the Visual Algo site. Okay. It's pro con, right? It's actually not a bad algorithm. It's pretty similar to the DFS one. Okay. There are certain costs that we might incur that might be a little bit more or less than the other one. But let's look at the Tarzan one since we have studied the DFS a couple times. So again, the idea is for each unvisited vertex, let's begin a recursive traversal of that. And then for each neighbor of that U, okay, so these are the adjacencies. If it's unvisited, we're going to go in, order of the adjacency list. So you can think of it as left to right order, I guess. But we're going to call that recursive call again if it's unvisited. Otherwise, we'll skip it. And this is the key part here. After we return from a recursive call at a particular recursive level, we will then push this U onto a stack. So this is the reverse part of our post-order traversal. Okay, and we will look at the actual code for this in a second. But we often forget that we can do things on the unwind that give us a pretty unique result. And so in this case, the unwinding from the recursion is where we collect that U on the stack. And that gives us that bottom up kind of topological sort. Okay. So after all is done, after we've done this thing for every possible vertex, we just unpack the stack. And now we have our topological sort. Okay. So whether it's, 5 classes or 5 million, vertices, we can kind of use this algorithm on this thing. So let's try to track this thing through on this graph we looked at previously. For each vertex, we'll just start with 0. We have no idea where to start, and it does not matter where we start. So we're just going to follow the vertices in order. We start at 0, do a depth first search on the graph, right? We know it has no cycles. That is a given. If it has cycles, it's going to break. So let's assume for the moment there's no cycles in this graph. So we're going to perform that depth first search until we visited everything and return those vertices in the reverse post order. Okay. So and on the unwind, we'll add that to our stack. So I thought I had this animated. Okay. So we go 0, right? Then we go to 1, and we go to 4. That's as far as we can go. Okay. So now we're going to unwind and we're going to put 4 on the stack. Okay. So imagine yourself, you're at, 2 levels down recursively and you're getting ready to return to the upper level. But right before you return, you say, okay, I'm at 4. So I'm going to put that on the stack. So you basically traveled as far away from home as you can. You're getting ready to return. You put the 4 on the stack. Then you put the 1 on the stack. And you're back up at the 0 and you're not done yet. So now we're going to go down again as far as we can go. We get to the 2. That's a dead end for us. There's no arrows going further. So we unwind and put the 2 on the stack. Okay. Keep going. We got a 5. We try to go to the 2, but the 2's already been visited. So we just put the 5 on the stack. Okay. And go back. Okay. So 2 is visited. We have that was visited array. Okay. And then we finally get to 0, but we're not done yet, right? That's just the dependencies that we got by starting at 0. So now we try 2. Well, 2 has already been visited. Now we try 3. Okay, 3 has not been visited yet. So let's start our DFS on 3. Okay. Again, very similar to the constructor in your Connect component class. So now we try for 2. Already been visited. 5's been visited. 4. Okay, that's been visited. 6. Okay, 6 has not been visited. So we will follow the adjacency list. Okay, 4 has already been visited. We're done with 6. We're not done with 6. We got to go to 0. Now we're done with 6. And we unwind. And that is our topological sort, right? We unwind back up to 3. So 360521 is the order in which we would take these classes. And there are multiple possible correct answers, okay? It all depends on the ordering of each adjacency list. In other words, if 0 had the first adjacency as a 2 and the second one as a 5, we would have traveled down the 2 first instead of the 5, okay? So the way we construct the graph is going to affect the topological order that comes out of this algorithm, but it's still going to be a correct answer, okay? So if we all build our edges the same way, then we'll all come up with the same topological order, okay? So that's the Tarzan depth first search algorithm kind of without code, okay? Questions? Yeah, I promise we'll look at the code. Okay, so yeah, when we unpack that stack, that's, one order, okay? Okay, oh yeah, and by the way, this always confused me. The terminology of this says that if A is a prerequisite of B, then we often call B the dependent of A, okay? So that to me is confusing because I feel like a prerequisite is not dependent on the class that follows it, but in graph theory language, we refer to the thing being pointed to as the dependent, and this is the predecessor, right, or the prerequisite. So this terminology I find confusing sometimes, but the prerequisite always points to the class that follows it. That's maybe a rule we can all relate to reasonably well. Okay. Okay, so if you start to get disoriented, all right, we're going to use the C++ stack for this implementation. It's pretty clean rather than building our own. So we create a stack of integers, we push integers on it, we check what's on the top so we can see what it is, and then we pop it. So pop does not return a value, it just gets rid of it. So we have to peek at it and then pop it, okay? So top and pop for our C++ stack in our code, okay? So here's our depth first order class. We're going to create a class that, like the path class and the connected component class, is based on the graph. We need a was visited. We need a stack that we can fill up when we unwind. There's our constructor. Somebody gives us a pointer to a graph. We will call the graph to get its vertex count and build our was visited array. And we will initialize it, and then we begin our depth first search. So for each vertex from 0 to the less than the vertex count, if it wasn't visited, drop down recursively into the DFS method, okay? And our DFS method is part of this class, okay? So we're building up multiple DFS methods. There's one in the path class. There's one in the cycle class. We've got them all over the place now, okay? So let's take a look at what that is. So that constructor there basically builds the was visited and then populates the reverse post stack. So when our constructor is done, we now have the answer to our question, okay? That's just one kind of side behavior of this. Like once the constructor's done, we have our answer right there, okay? So it's being built as we're unwinding in our depth first search method down there, okay? So let's take a look at the code, and you can think about this in a very, very simple graph situation. We have a prerequisite 0. You take class 1 or 2 after that, and then you could take 3, but 3 can only come after 2, right? You can't go directly to 3, so we're going to need a topological ordering that's something like 0, 1, 2, and 3 has to come last. It's sort of obvious from this, but it wouldn't be obvious without those numbers necessarily, okay? So we're going to follow this algorithm. Let's just jump in, and you can use this data. There's a bunch of sample graph data in the comments at the top. So let me open that up here real quick. Oof. It's the first time that's happened. I hope I'm not crashing. If I do, we'll pause the recording and come back as quickly as we can, but that's not a good sign. Oh, good. Okay, whew, that's lucky. All right, so here's my graph class all ready to go. Here's some sample graphs up here. You can just, paste in. This is the vertex count, followed by the pairing, followed by the negatives to terminate the input cycle. Should produce these topological orderings, okay? So if you want to just grab one, you can kind of paste it in there. I'll grab this one here. The easy one that we had in class, I think the simplest one is probably this one here, I think. Oh, by the way, well, yeah, let's just go down and do the code first. Okay, so graph class is there. Let's go to our way down there, past the graph class to our depth first order. Okay, topological order. So we're going to do an integer stack. So we're collecting vertex IDs. So that's our stack inside of our depth first order. Okay, and we want to say, okay, if this particular vertex was not visited. So not was visited, square bracket, VID. So if it hasn't been visited, then let's go visit it, okay? Okay, so let's take a look at our DFS. So immediately we mark it as visited, we get its adjacency list, and for each of its adjacencies, we're gonna say, if that thing wasn't visited, then let's go ahead and visit that, right? So that's just TV arrow ID. So it's a pointer to an instance of a node, and we're traversing through all of the adjacencies, whoops, okay? And when we get back, so that is part of this for loop, right? So this is us visiting all of the adjacencies of where'd it go? Of VID, okay? So we're visiting all of the adjacencies recursively of VID, and now we're going to put VID on the topological list, okay? So this happens after this whole set of adjacencies has been visited recursively, okay? Assuming they were not visited. And that's it, and we're done, right? That's the end of our DFS journey. And then we just have some utility methods. We can return the reverse post stack, or we can just print out the topological order by deconstructing a copy of the stack, okay? So let's go down to main and see if there's anything else we got to do down there. I think down in main, rather than doing all this stuff, which we've kind of got a method for that now, I'm just going to say dfo.print topo stack. I think that's what it's called. We call it print topo stack. Sorry, print topo order. Print topo order. Okay. So we're saying go ahead, create it, and then print the topo order. All right. So let's see how we do on that. Okay. Okay. There's a little garbage character at the top. I think that snuck in on me right up here on line 38. So sorry about that. You guys probably have to delete that one there. Okay. There we go. So how many nodes do we want? Let me grab one of these sample graphs. So I'm going to grab this graph right here and just paste the whole thing in there. So vertex count and then all of the connectivity. And it's going to go through all of its graph building and it's going to spit out the topological order. Okay. So 0, 2, 3, 1, and that is this graph right here, 0, 2, 3, 1. That's a valid topological order, okay? Now notice I could have easily done the exact same graph, built a different way, and that is here as well. So I'll go to this same graph, right? And notice that the result is going to be a different topological order. It's the same graph, it just has a different construction order, okay? And so if we run that down and we look at the bottom, we get a valid answer, but it's not the same as our first answer, right? 0231, 0213. Both of them are correct order in which to take our classes. So there's nothing wrong with the answer. It just happens to be one of several correct answers, okay? So topological sorting is kind of a foundational building block in other algorithms. So it seems pretty dry most of the time, which is why it's kind of hard to make it exciting. But once you can do it in a directed acyclic graph, you can solve some really, really interesting problems. Okay. And one of the interesting problems we can solve with this is the strongly connected component problem, which we will be taking a look at in our next lecture. So we will be basing, other things on top of this depth first order class. Okay. So here's our here's what we just looked at in code. Whoops, sorry, I missed my last curly brace down here. Okay, so I should have another curly brace there, right? So we created the graph, we had an input loop, created the depth first order instance, which then created the topological stack for us so we can print that thing out. And I think, let's see if there's some key points. Oh, and we could have manually deconstructed the stack. This is just kind of unnecessary. I could have said, hey, go ahead and get me the reverse post stack. I'll get a copy of it and then I'll deconstruct it, piece by piece and print it out as I go. But we just had a nice method for doing that. So this is the more manual way of doing it. Okay. Now the stack isn't absolutely critical. You could put it on a vector. So you could just append these things to the end of a vector and then, list the vector out from position 0 to the end. So it's traditional to use a stack, but you could also do it with a vector if you wanted to. Okay. And there's our kind of, all the code that we updated there. Okay. Questions on topological sorting? Okay. So key points. It's got to be on a DAG, and it's going to be on a directed graph. Okay. Because we don't want any cycles. So we need to ideally figure out whether it has cycles or not. And we're going to use this post-order traversal for the Tarjan algorithm. Okay. And there can be multiple correct answers. We're only really finding one of them. Okay. And our construction order will change what our answer is. Okay. So we might be able to get a topological order using the Tarjan algorithm, but it won't be correct if we have a cycle. We might not even know it, right? It's not like it's going to necessarily crash or go into an infinite loop. So if we don't first check our graph for cycles, then we actually could end up with an incorrect answer. So we do need an algorithm then for how to find a cycle. Okay. So that's kind of where we're going to go next. Okay. Deep breath. So if you want to take a look at these examples, once again, Quizlet Q7 has a lot of pictures, and I do use these pictures in our quizzes. So recognizing or just being able to finger trace through these graphs is kind of important to understanding the algorithm. So you can kind of pull those things up. And some of them will have audio, so you can kind of play it back if you need an additional description of why. Okay. But you'll certainly be seeing these questions on quiz 7 coming up, right? Okay. And here's what that's going to look like. Identify a topological sort for the graph shown. Okay. So you'll be able to click on the graph over here, see a big version of it pop up, and then you'll be able to kind of identify, given that prerequisites point to the class you take after, you'll need to identify, whether it's got a cycle, then it's no solution. If it doesn't have a cycle, you have to identify what's a valid ordering of those vertices. So this is one of the ways we'll kind of evaluate your understanding of this topic for the quizzes. Okay. Okay. So this is just all, different ways of executing Quizlet, which if you play around with it a bit, you'll figure out you can use flashcards or matching or other things, multiple choice. Okay. All right, let's see if we can tackle the finding cycles one. We don't have a lab today, so I'll get you wrapped up here, I think in the next 15 minutes or so. This is not a huge topic, but it once again does require that we use depth first search and recursion in some interesting ways. And again, the reason we care about finding cycles, at least in one case, is for this topological sorting, okay? So we don't want to try to apply Tarzan's algorithm unless we know it's truly a DAG, okay? So, and there are other algorithms that rely on finding cycles too. So it's kind of another building block in our list of important algorithms we want to be able to solve, okay? So not good in that situation if we were doing a topological sort. Okay. So let's talk about how we would use depth first search to find out whether something has a cycle. So if I do a depth first search on some graph G, starting at vertex 0, I'm going to mark each vertex visited as I see it. And then I'm also going to put it on a recursion stack. So I'm going to keep a little scratch pad that says which vertices I have visited in my recursive traversal. So normally we don't really have access to the function stack, right? Some of us know when you do recursion, you have stacks of function calls on top of each other, or stack frames. But we're going to manually create some information that says, hey, I visited 0, then I visited 1. And when we unwind, we have to clean up that recursive stack ourselves. And that recursive stack is how we're going to know when we've encountered a cycle, okay? So there's whether I visited something, and then there's whether that thing is also on the current recursive stack, okay? So this is a crucial part of what we're adding. So for each dependency of some adjacent vertex to 0, right, or everything adjacent to VID, if it wasn't visited, then I'm going to record how I got here. So that's the from vertex path. And then I'm going to drop down again, okay? If it was visited, I'm going to check and see whether it's on my recursion stack, okay? So this is, sorry, not was visited. This is my putting it on my recursive stack, right? So I'm putting it on there. If it was visited, I'm going to check and see if it's on the stack and in my recursive travels, if I've seen it, right? So for example, if I am here and then here and then here, and I encounter this, it's been visited, but it's also on the stack, that's a cycle, right? And that's a bad thing. So that's how we're going to use, sorry, that's my unhappy face there. That's how we're going to use our stack. And then before we unwind, we're going to remove this current VID from our recursive stack so it doesn't hang around on some other recursive journey that we're going to take. So in addition to keeping whether something was visited or not, we need to know whether it's on our recursive stack, okay? So let's see if we can trace this algorithm through with this particular graph, okay? So I think I'm going to animate this, right? So if we travel down here to the end of 12, right? And then versus traveling down to 12 this way, we visited 12, right? So if I do this recursively, this is just making a key point here, and I mark all these as visited, right? And then I come down here and I discover, hey, this was visited. That does not necessarily mean we had a cycle, right? Because I kind of came down this way and then I erased my recursive stack and then I came down this way, okay? It's still visited. It's just not on my current recursive stack, okay? So that is not a cycle. So that's what we're saying here. It's not enough to ask, was it visited? We need to know if it is in the current stack for our recursive travels, okay? And each time we do that, we kind of clear the stack. So here's our data we have to keep. From vertex, was visited, and is it currently in my recursive stack, okay? So let's sort of trace this out. So I go 0, right? And then I have a from vertex of -1, right? I come down here to an 8, right? I got there from the 0. I go to a 10, okay? And I realized, okay, I came to a dead end. This is not a cycle. So I clear out my recursive stack markers, okay? So the stack in this case is just, is it currently something that I have visited on my current journeys before I unwind? When I unwind, I clear out that on stack thing. Now I go back and try another child of zero because I'm still working from zero. So I go to one, right? Okay, visited, all right, from vertex on stack, right? 9, visited from 1 on stack, okay. 3, visited from 9 on stack. 2, visited from 3 on stack. And here's where we find our cycle. We say, okay, I came to this. This is already visited, right? And it's on the stack. So if it was visited and it's on the stack, boom, we know by definition we have a cycle. Okay. So this is the extra piece of information coupled with this that allows us to do that test. Okay. We can't do it with just was visited alone. So let's take a look at what that looks like. So once again, we're going to create a separate class. It's going to have a constructor where we get a graph. We're going to create our dynamic elements. We're going to initialize them, right? And we will follow that hopefully familiar pattern for I equals 0 less than vertex count. If not was visited, recursively drop in and give you the I, right? Right there. Okay. So let's take a look at how we've changed our DFS slightly again. And remember that this is going to be empty unless we find a cycle. If we find a cycle, then we will inform ourselves what that cycle was. And we're only finding one cycle before we give up, right? So at most one cycle. We're not going to find all cycles, just one cycle, okay? So here's the has cycle. These are the other methods, basically. So if it has a cycle, right, then the cycle data member will not be empty. And then we can just get a copy of that stack, okay? So this could be a vector. It could be a stack. We're just kind of using the stack for this one, okay? So these are the other methods. We're going to dig into the DFS method next, okay? So we're going to work with this graph again. Okay, this graph has a cycle. So it's got 5 vertices, okay? 5 vertices connected this way with a cycle there, okay? So we'll use that to test, and it should produce a cycle 2, 3, 4, 2, 2, 3, 4, 2, okay? We should see something like that come out of this. So let's see if we can finish the code here. This is our last one for the day. Be careful so I don't ruin it. Okay. All right. So let me find my to-do. Okay. So we're inside of the depth first search. Get rid of some of this stuff here. And we've been given a graph. We're inside of our new class. Okay. Directed cycle. Okay. And our constructor for directed cycle is calling us DFS. Make that a little bit bigger. I know it's kind of annoying. All right. It's calling us. Here we are. A little emergency code looking for bad data. But otherwise, we're going to say, get the adjacency list of VID, right? The thing that we're being asked about, okay? Then we're going to loop through that. Oh, first off, we're going to say, okay, it goes on the stack, right? On stack, VID gets true, okay? So that is now in my recursive journey. Now I'm going to drop in, and if turns out I already have a cycle from some other recursive process. This is a crucial base case that isn't immediately obvious. I want to bail out. I don't want to keep going trying to find more and more cycles. I just want to stop at the first cycle and return, okay? Now we could try to find all cycles. That could be done in a brute force way here, but we're not really trying to tackle that problem right at the moment. The rest of this is what we do if we didn't already find a cycle. So this wasn't visited, then figure out how we got here. And then we want to recursively drop down, right? So DFS on G, right? DFS on G with that particular adjacency, okay? Now, when we return from all of that stuff, right? That drop down, okay? Or sorry, else if, right? If it was not visited, we do that. If it was visited, we got to check and see if it's on the stack, then we've found a cycle. And we push that vertex onto that cycle list. And we're going to search backwards through the from path to build up the specific cycle that got us here. So this is the little squirrely part. So X equals from vertex X, I believe. Right, so X equals from vertex X, right? So we're working our way backwards using the from vertex and pushing that information onto the cycle found. And then we push the origin vertex on, and that should be our full cycle path, okay? And on the unwind, we have to say VID gets false. Remove that thing from the stack, okay? So that's us unwinding up the stack. Whew, okay, so let's see if there's any other key steps here. I don't think there's anything that needed to be done down here in main. Let's see if we got a compile on that. Nope, cycle stack pop on 397. Missing a semicolon there. Okay, pop possibly parentheses and a semicolon. That would make more sense. Okay, so let's try one of our sample graphs. Sorry, one more time up to the top here. I'm going to grab one of my examples. So 5, right, should produce a 2, 3, 4, 2. Okay. Looks like crash. Okay. And 2, 3, 4, 2. There's my cycle. Okay. Okay. So the whole thing is really not too different than, again, what you're doing in homework 7. We just have this little extra piece of logic where we are adding things on and off of our trace of our current recursive stack, okay? And then resetting it before we return, okay? On the way back up on the unwind, okay? So update the VID, process the dependencies, bail out if we've got a cycle, drop down to the next level, and record the cycle if we found one, okay? Whew, that one's kind of gnarly, okay? And then here's the full answers to that, right? That was the hint, and this is the kind of the final answer with everything filled in, okay? So let me see if I can get us out of here a little bit early. So easy change to our graph to support directed graphs, okay? So we can do both now with a minor change to our graph. All of our path stuff still works, just like it did for finding shortest path or any path. So that's pretty straightforward. And there are a new class of problems that we're going to need to learn how to analyze that are a little trickier with digraphs than regular undirected graphs. Solving this prerequisite problem is the first key step in solving a lot of other harder problems, as we will see, okay? So that's our topological sort. And finding cycles allows us to do that because we can't really do that in a graph that actually has cycles, okay? So we've created this directed cycle class to help us do that. So next time we will dig into how to determine these islands, right? So how many components or how many strongly connected components is really what homework 7 is all about. And so we will kind of study those with a new algorithm that depends on this topological sort, okay? And it's called the Kosaraju-Sharir algorithm, okay? Named after the folks that invented it, okay? So this is a strongly connected component, right? Because they can all be reached, right, by each other, but we can't do the same with one. So one's kind of floating out there by itself, okay? that's what we'll talk about next time. Okay, and that's it. No lab tonight. I'll stick around and help folks if you have questions on your homework. Otherwise, I will see you on Thursday. Okay, let me go ahead and get rid of stop our recording and our share. And thanks.